today, since you guys are gonna have time during the break to start working on your projects, and one of the objectives of your projects is to put the model in a turn the model into a NanoHub app. We will walk you through how to create some interactive features in NanoHub, how to couple it with Tellurium, and then how to sort of test your code as an application. Some of this stuff is stuff that we are still also trying to figure out ourselves. So we'll be learning with you as we worked on this a little bit. Just in case we get stuck or something, you guys sort of like understand where we are at. The specific interactive tools that we will be using are called the Jupyter Widgets. The documentation is available here. And we will keep referring to this so you guys have an idea of what are the interactive tools available to you. Yeah, that's it. We'll just see this in more detail. As I mentioned, we're gonna use this. We're gonna introduce these Jupyter sliders, and we're gonna explain them in the context of the replicating the within host models that we were working with last week. Some of the stuff that we're gonna discuss in class go over a couple of the exercise for the homework, yeah. So you'll get an advantage if you're also working at the same time in terms of getting at least 2 or 3 of the exercises for the homework done here in class. Last time so yeah, James made a good point. We will not just how to create interactive tools, but also how to manipulate your notebooks, so you can include text in your notebooks and images and sort of and all of that kind of stuff, which makes your, not just in terms of developing your app, but for example, when you are working on your Jupyter notebook, you can actually use it as for texting, adding comments, documenting your work, such that you can keep track of what you're doing, and then when you submit an assignment, the assignment has the explanations on your Jupyter notebook, and then when you create an app, you can include text that comes along with the application. Last time, one of the models we were replicating was the hepatitis B model with a logistic growth. And we showed that as we increase R0, we go from a system that has just a fixed point steady state that has no oscillations, to a system where you have stable oscillations. And we showed that those oscillations increase as you increase R0. And after certain points, the amplitude, those oscillations disappear once again after increasing R0 after a certain point. We talked a little bit about what this transition meant. In dynamical system theory, that it's called a bifurcation. It means that as you change your parameters, the value of your parameter, the steady state of the system changes. You go from a fixed point steady state, meaning that you have a fixed value at the end. If you run the simulation for long enough, you end up at a fixed value. And as you increase R naught after 7, in this case, instead of a fixed point, you have stable oscillations, where the system oscillates between two values, and these are the values shown here in terms of the amplitude of x and y of x and y. We will some of these exercises we didn't get to do in class during the replication in class, but we will work a little bit on it and show how we can measure the periods of the oscillation as a function of R naught and the amplitude. And then the second model that we worked on was an HIV competition model between a mutant and a wild type vital strains. And in that case, we showed that there is a combination of the reproductive ratios R of both viruses that produce different steady states. There is a region in the space that where the mutant virus dominates, which is the red one here. There is a region where both viruses coexist, and then there is a region where the infection fails to propagate or take on when the reproductive radius of the viruses are smaller than certain particular values. And in class, what we did last time was that we picked certain points in this space and showed that the system had qualitatively different outcomes, or the steady states vary as we change the values of these parameters. Today, when we go to the yeah, James, definitely. We can, when we break up to the, there's a couple of stuff that we can do when we break out when we go to the breakout rooms. But an idea here is that instead of we first have to show what happens when you change this consistently and create a bifurcation plot, and you should see that the values change. As for example, for a fixed RS, what happens to the steady state of the viruses as you change RR? That would create a bifurcation plot in this following a line here, and then a bifurcation plot in this direction. And then we can make those bifurcation plots sliders, so we could slide the line to see how the bifurcation behaves as you move the parameters. So that is something to work on the breakout rooms, though. Okay. So what I'm gonna do is I'm gonna minimize this window, so we have an idea of what is the model that we're working with, and I'm gonna move this way. And the idea here is that I'm gonna introduce the use of sliders, how sliders can be used, how sliders can be combined with Tellurium, so you can play with the parameter values interactively. Then we might actually, it depends. We can break out into break rooms and work on those stuff that we haven't done, and stuff and ideas that James also has. But it would be also it would be interesting to go over the documentation of the widgets, because you guys have an idea of what your projects are already. And then looking at these widgets, you can get up an idea of what kind of interactive tools might be useful or not. And I can show you what I've been working on with the SIR model that we worked at the very beginning. We've been working on developing an app for that as well. Okay, but just as a teaser here, so we have this. We've implemented this model as an anti-money string, and following the parameter values of the paper for here and here, we show that we can replicate those results. That for an R value that is for this particular value of R naught, which doesn't necessarily correspond to this plot because the parameters are to these values because the parameters are different from this plot, for this plot, and then for this plot. So they have different parameters for all of the plots. But the idea is that below a certain parameter value of R naught, there is no stable oscillations at the end, or there is just at one fixed point at the end. Fixed point meaning what is the stable value of X and Y. X means the healthy hepatocytes, and Y is the infected hepatocytes. And then as we increase R, there is a threshold above which what we get is stable oscillations. So instead of having one value, what happens is that the healthy hepatocytes and the infected hepatocytes oscillate around certain values. So what we want to do first is to be able to, here we're manipulating this the value of R naught. Basically, we're hard coding it, and we could create multiple of these plots, one after the other, to show. We could do something like we could do I don't know. We could do something which would be kind of, which is sort of like what we've been doing so far, but it's not necessarily very pretty. We could do something like this, where we iterate through.
Not an integer.
Yeah, it's just that those values of G are not necessarily good. But let's see. No. Let's do still. $360 to $280 to $360, because we know. Why am I getting a?
How is G defined in your model?
Here.
Should be okay. Let's see what the error is throwing is.
Right here. So we could do something like this, where we start manually changing that's for values. Let's see. I don't know what that error was. I didn't change absolutely nothing. So we could do something like this. Is kind of like what we've been doing. We've manually been changing the values by iterating over a by creating a loop and seeing how's that changing the parameter values. Right. but that is not interactive, right? That is not it's just creating a bunch of different images for each of the parameter values that I'm choosing. Oh, by the way, I forgot to mention that this this Jupyter notebook that I'm using, it's available in the folder. It's called Lecture 13 Demos. So instead of doing this way, we would much rather do it interactively. So as allowing to interactively change R0 and seeing what's happening. And just as a teaser, I'll walk you through the code. So this is we were playing with this a little bit, but I'll just have the same. Just as a teaser here, instead of doing it that way, I can have an interactive way of changing the parameter. Let's call it. This is what you were saying, James. R0. So now I can interactively change R0 and see what happens as I increase the value in real time. And I can see that I go from a regime where I have the oscillations, a regime where the amplitude on the oscillations increases, and then a regime where I get no oscillations. And then if I decrease R0, and this might be slow because every time you change R0, it's rerunning your model. But you can see how we went for a region where we had oscillations to a region where we have a fixed point. And then if we decrease R0, then we go to a region where we have no infection happening. You can see that the healthy hepatocytes always stay the same, and the infected hepatocytes always stay at 0. Okay. So, okay, what I'll do is I will explain how I'm wrapping this in the let me see. I'm torn between explaining whether I should how to wrap it or explain what type of widgets are available. But I'll walk you through the basics, and then we can. Yeah, okay, that's a good question. Has anyone used this type of interactive tools before? Okay. Okay, so okay, so okay, cool. So the easiest way to, and this is relevant for you, for your project. This is the documentation page for the widgets that are compatible with Jupyter Notebooks. This is, I mean, there's other packages as well. Matplotlib has its own set of widgets, but I think IPy widgets are very user-friendly in terms of how compact the code can be. So in terms of, you don't have to install it because it's already available to you with the Tellurium application when you launch it on NanoHub. The easiest way to use sliders is to use the Interdac function. And this Interdac function is quite powerful. So it's very easy to work with it. The way it works is that Interdac always takes a function and then the parameter that is gonna be an input to that function. So in this case, let's just, yeah, this is the best way of doing it, so I can explain this later. So let's just create a new cell below this. So what I'm saying is Interdac I have to import from from IPy widgets. I need to import Interdac. So Interdac always takes.
Josh, maybe share the URL in the chat for the manual.
Yeah, and James has a good point. Not all of them are available in NanoHub because of there might be difference in the version installed in NanoHub and the latest version that it's gonna be the document display for the documentation. But that is I'll show you how do you explore this in terms of looking at what widgets are available to you. But what I'm in terms of the basics, Interdac always takes in a function and then the parameter that you're gonna take, the parameter that you're gonna enter, that is gonna be an input to that function. So let's just define the function. And just to have something, that function, it's gonna print the value that I'm passing on as from the slider, right? So
do
now
you want people to follow along and do this while you're doing it?
Yeah, please.
Do you want?
Yeah, because then we can explore. Then we can explore a couple of the widgets here.
So why don't you give everybody just a minute to launch Tellurium and.
Okay, fine.
Give a thumbs up when you've got Tellurium running.
Or I can send a poll. As I said, this version of the code is uploaded in the James, can you share the link to the lecture 13 demo folder? Okay.
Please check them. If there's a problem with that link, let me know.
And again, we haven't, in terms of the code, we have just executed it. I just changed this part to show what, to show that, and you guys at this point know how to do this in terms of reloading the model and just plotting it inside a loop. But now, and then as a teaser, I presented what we did here. Now we're gonna try to build it from scratch with you, so you guys have an idea of how it's working. So don't worry necessarily about it right now. We'll come back to it. We'll construct it together. So okay. So, and I'm just gonna copy and paste this in the chat in case you guys want to just follow. So you guys can follow from here. So as I was saying, Interdac takes a function and the widget. Here you have a lot of, since Interdac is a very powerful tool, you have different ways of specifying the widget. Interdac interprets certain formats as specifying a widget, or you can create the widget independently. We'll do both. But if you just pass let's say a particular value, x equals some particular value, it automatically creates a slider for you. And then
if the initial value is an integer, it creates an integer slider. If the initial value is a float, it creates a float slider.
Yep. Then
and if it's a string, it creates a text box in there, the string.
Right. So if it's a string, it creates a text box where I can enter something. If I pass a list, it creates a drop-down menu. Okay. So for example, if you wanted to create, and we'll see it later, if you have different data sets and you want to give the user the opportunity to load different data sets, you can use this drop-down menu to give the user the option of what data sets are available to them. We will do that. I'll show you an example later on. But yeah, so here's the couple of examples. If you pass it a true or false, then it generates a checkbox. And again, you can pass not just one parameter, you can pass two parameters. Of course. So now I have two parameters that my function takes. And then this is returning the value that I'm passing and whether it's true or false. Okay.
Can everybody try to replicate that? Because that's actually, if you could do that, you've got a lot.
And this is just at the this is just the first couple of examples in the documentation. Okay. Okay, good. So, okay, good, everyone got it. Yeah, there is a lot of options for you. You can, as I mentioned, you can that is the 4 formats that Interdac will interpret from how you pass the options. But there is multiple other widgets that you might want to include or not, depending on what is it that you want. So I could, because of that, I can define the specific widget that I want, and also the specific, if I want to add more options, right, I can do so as well. So for example, so when I pass X, right, and I pass just one value, the step size is fixed, right? It's 1, it's an integer. And the maximum and minimum values are also fixed. It's -20 on one side and -20 and +20 on the other. But I should be able to be, I probably want to control both the step size and what the upper and lower limits of my widgets are. So to do so, yeah, I think, yeah, in that case, I have to use the widgets, the widgets abbreviation. So if you wanna have a full an idea of what all the widgets that are available to you, you can go here to Widget List, and then that has examples of all of the options that are available to you when you in terms of what are the widgets that you can use. And I'll show you a couple of those as well. We can come back and see a couple of them. But in this case, we're just gonna specify that we still want this integer slider. We still want this integer slider, but then now I can control what the maximum, minimum, and the step value, and the step size and the value of that widget is. Wait, what? So wait, do I have to? No, because oh, hold on, I'm sorry. So I specified the widget outside of my Interdac function, and then now I have greater control over what are the ranges and the step size of this that the slider is going to have. Let's say I want a step size of 5, and the minimum and maximum is going to be 30. So now when I change, I go up by 5. That's the step size, and I go up to 30 and down to 0. Okay. And then if I wanted it, instead of instead of a integer, I can have a float slider. And then now I say that I want my step size to be 0.1. And now I go, as I move my slider, it goes up and down by 1.1. Okay. Let me see. So, oh yeah, so here is an example of what are the ones that, so for example, I lied, and not lied, but there is a way of not having to specify the slider this way by passing certain types of, if you pass a tuple, you can summarize this by passing a tuple that is 0, 32. Hold on, let's see. Right. So here it specifies how you could pass this, right, as well. You can do it either this way, or it interprets whatever you pass to the parameter depending on this. But this is limited, right? This is just the limited. It just has 1, 2, 3, 4, 5 options, and it's limited in terms of how much control you have over what the widget is doing. So I prefer this way because I have much more control over what the widget it's gonna be and how it interacts with my function. But for basic stuff, you can do it this way. Okay. So let's see. Let's keep walking through this. Yeah. So I showed this one already. Okay. This is just in case when I choose from the drop-down menu, instead of passing the string, it passes a value. But you guys can play with this. You can play with this by your own and get a sense of how to specify this. I'm not gonna go into what Interactive is doing because it's just an extension of Interact that allows you to have a little bit more control. But you should be able just to play with Interact to get a sense of what it's doing. What I'm going to explain now is how we wrap the Interdac function with the Tellurium function, and then we can come back to the widget list and play with a couple of that to see what are the options that you have right now. So now that we have this, we know. So the question is, how do we combine the slider with the Tellurium model? And anyone has an idea? I mean, you guys can see it in your code, but I want
you can also unmute. You don't have to stay silent.
Right. So the idea is that from the widget, you get as you modify the widget, you get whatever input you're specifying to the widget and in the widget, right? So what we can do is that take that, in this case, a particular value, and use it to update a parameter of my model, simulate the model, and replot my model with that particular parameter value. And then what that's gonna do is that it's gonna allow me to interact with the model in a way that connects a slider to a parameter in the model. Okay, so what we're gonna do is we need to, James, I learned about Interdac yesterday, really, because I was using the previous version that we had, but this is very compact. So we need to define our function, and we're gonna call it replot, because it's gonna be, what the function is gonna be, is gonna be resimulating and replotting the model with a specific parameter value. And the parameter value that we're interested in this case, if we come back here, is R0, right? That is a parameter that is allowing us to go from a region that has no oscillation to a region that has oscillation. So we're gonna go call that parameter R0. We need our model.
Maybe paste that into the chat too.
Yeah. So so what I'm doing is I'm just to explain really quick. R0 is not a variable of your model, right? It's R0 it's a value that you get by combining some of the parameters of your model, and that is telling you the reproductive ratio can be determined by the of the model. So what I can do the reverse as well. I can, if I have a particular R0 and I have all the other values of my parameters, then I can specify certain one of the parameters of my model in terms of R0. And what I'm doing here is that I'm specifying my parameter gamma here as a function of R0. Because you have a better sense of how R0 should control your system, it's better to specify it, right? Yeah, it's beta times gamma over alpha times mu, and yeah, right. So since I have that relation, I can choose to specify any of the parameters of my model as a function of R0, as long as I fix the other parameters. So what I'm doing is that I'm gonna solve this for gamma, and then I'm gonna specify gamma as a function of R0. So I define gamma as I define gamma, literally what I just said, as a function of R0 and the other values of my parameters. So what I need to do is that this function needs to load my model, or potentially can reset it. It doesn't matter. I don't know why you always use load instead of reset. That might be in terms of making it computationally faster. You might want to reset rather than load, but just do this.
That's something you could check out. Is it run faster if you load it outside the loop and then do a reset?
Right. We can put a timer and do that. We'll do it here. So now, once I load the model, then I can define R0, which is a variable now in my model, as being the value of the parameter that I'm passing on. And remember, this value is going to be passed on from the widget. Then I'm going to simulate my model. And if I look at this, they simulated from 0 to 800 days. I'm going to create 1,000 points. And the specific variables that I'm interested in, since I'm plotting this, is I'm gonna plot the healthy and the infected hepatocytes. And then I can just plot it. Let's just make sure. Yeah, I'm just fixing the limits because of the oscillations. You really want to have a better sense of how the oscillations are changing. So you have to fix your axis, because every time you simulate the model, and that plot is going to adjust the axis of your model to fit the data that you have nicely. But if you want to really have a sense of how the model is changing, it's better to fit those limits so that they don't change as you change your slider. This is small details, but they are important if you want to get a better sense of appreciate how the slider is modifying your model, is controlling your model. And yep, and if we want, yeah, we don't have to do that. We'll just print our none. I'm not sure if the slider already reports it or not. Okay, so now we have created the function. Again, the function, what it does is that every time I change my slider, it reloads the model, assigns the value that it's getting from the slider, simulates the model, and then plots my variables. So all I need to do now is to use the Interdac function, and let's just do the easy version. So we want a float slider that goes from R0 0. Let's go from 0 to, let's go 13. And the size, so here the size we can play with, let's do it 1.1, 0.1, and we'll see how you might want to play with that value or not. Okay, and if I do that and I execute it, then it's available to me. So
why don't you make sure everybody could repeat this? I think this is important that everybody have the same. You could. Why don't you share the code, just the antimony string, and then people should by hand reinvent that part of it.
And I'm gonna come to a little bit of, in terms of how to make it more user friendly. I'll talk a little bit about it. But that is right. That is, it's more on when you care about the user end of your application. I'll just give like a couple of more seconds.
When you've done this, this might not be a bad place to do two more little things. One of which would be, instead of plotting X and Y versus time, to plot X versus Y on a plot. And then also to add a second slider that doesn't just change R naught, but also changes the initial value of Y.
Okay.
As a percentage of the initial value of Y as a percentage of X. Okay. And see what it's called an orbit. Right. Which is what you see here in the bottom right-hand corner of this.
Right.
So that's something you could do now with one or two lines.
Yeah, that's quite easy. I think for that specifically, I don't know how to use the mplot to do that, but I'll use the Matplotlib library to do
that. You could use plot array.
Oh, I could, right.
And just pass it the X column in the Y.
So plot array is basically making the Matplotlib library available to me. Yeah.
Right.
Okay. So, but before heading there, I just I wanted to talk quickly about some about how do you to think about the sliders in a way that makes it more user friendly. So when we chose the specific step size that we chose is it's kind of small. So every time you change it changes continuously. So every time you change the R naught, let's say from 3.5 to 6.3, it's going over all of those values that you went through and simulating the model for each of those values. And that might take time, and that is why you're seeing the delay from when I finish moving the slider to when it finally finishes uploading all of those. There is different ways that you can play with that. One of them is, of course, you can increase the step size. So you have less of those values to update between when you change the slider and the plots. If you come to the documentation, there is also a bunch of other options that might be useful to do this, but then you will have to specify them in the widget. So you would have to specify it as a different widget. And then I can use the template documentation. And that gives me much more control over so now it's not updating continuously. It just updates when I finish moving the slider. And you guys can play with these options to make sure that the way you're using the slider might be more or less user friendly.
You can also switch your mode to see what it would look like in a NanoHub app.
Right. And I'll show that really quick. If you click here in app mode, oh wait, I actually need to save it before doing that. Just always make sure that you save it before going to the app mode, because then otherwise it goes back to whatever you had at the, and of course I have an error. Oh, it closed.
Sorry.
I'll show later. It's okay. I have a version that works. I have a code that works. Sorry, I'm gonna have to relaunch this.
I derailed your talk. I'm sorry.
It's fine. Now everyone has time to catch up if they haven't. Okay. So yeah, as I was saying, then there is refer to the documentation if you want to have a look at what are the options that you might want to use in terms of having more control over what the slider is doing, how the values are updating, and there's a bunch of other stuff to control, and I don't know all of them. But by exploring the widgets, you can get a more familiarity with what it's doing. Okay. There you go. Okay. So now something James asked had in mind is if we look at these plots, we can see that there seems to suggest that if I plot this instead of looking at it in time, I look at it in the XY plane, I should be able to see something similar to these orbits that indicate whether my system is oscillating or not, or going into a fixed point. The fixed point will look like a point where where my line ends, whereas my orbit will look like a circle. So let's try to do that. With this. To comment this out for a second, and then I want to plot what I'm saying is I want to plot X against Y, or Y against X. And let's see what we get there. Index out of range. Which one? So yeah, I'm not super familiar with the has no attribute shape. Okay. Yeah, I cannot do it this way. think if I do it this way.
There's an easy way to do it, which is just get rid of time and use the plot or argument you already had.
Oh yeah, that's true. It's even easier, right? There you go. Why am I getting two plots? I'm not sure. Okay, there you go. So you can see that I start at this point, right? I start at a point where I have my initial number of x is 2 to e to the minus 11, and my initial value of y is 1. And then as time goes on, x decreases. Yeah, my value of x decreases and my value of y increases. Then they oscillate a little bit, but they come to like a fixed end here. That's what we call the fixed point, because it's literally a point in this plane. Then as I increase R0, you guys can see that those oscillations are increasing. And at some point when those two lines cross, that reminds me of my dynamical system class, yeah. Almost there. Well, even here, you guys can see there that it's at the end, it finishes, instead of on a point, it finishes in these oscillations here, instead of going into a point. It's hard to see, but the idea is that at the end, so I start at a specific value of x and y, and then instead of finishing in a point, I finish inside this circle here. Not this circle, at least this cycle is the right term. Yeah. So let's see what happens if I start instead of starting here. What happens if I start inside of this cycle? I think this might have been part of the assignment. I'm not sure. So that is 0.75 for x, for y, 0.75 e to the 11. And I don't know, here, 0.20 or 15 for x for y. dt. So you can see that in this case, oh god, it's moving a lot. Yeah, but in this case, I still. Why did I start, James? Why did I start in but went out and then come in? You're muted.
So I think the issue is that you have three variables because you also have the virus.
Right.
And so you don't know what the value of the virus is at that level as well.
Right, yeah.
You're starting with a 0 about a virus, so that's not equilibrated.
Right. If the system was 2D, then it wouldn't be able to cross that the limit cycle.
Right.
This is a conversation James and me, right? I'm sorry, but yeah, it took me right. The reason it's able to cross it is because you have the virus access that is not shown here. In the
So
virus
you could read off the viral load here, for example, and set that as your initial level.
Here.
So, for example, here your R0 is 9.4.
Right.
So if you read off the virus and start out with 2 10 to the 12 for the virus, that it should be about right. There you go.
Still crossing it.
No. Oh, because I didn't multiply right. It should be, let's see, it's 10 to the, sorry, 10 to the 10, 11, 12, 13, 10 to the 13. 2 10 to the 13. Yeah.
We're close, but not quite there.
Well, but it's still, you see it spiraling out now.
Right.
Well, that one's fine.
Yeah, but here's a good idea of what we're talking about, right? So now we are in this region of we are in a region where we have oscillations, and we start inside of these oscillations, and what happens is it's not pretty to see this way. This way is better. Here. What happens is that my system starts spiraling out and then settles in these oscillations at the end. So I think that might be, oh yeah, this is what this third point is trying to show. That when we start below the oscillations, then we circle out until we reach the oscillatory, the limit cycle. If we start outside of the oscillations, then it spirals in until we reach the limit cycle. That's called a stable limit cycle. This might be way too much, but yeah, this is really good. Then you suggested something else, James. You're muted.
No, I think that was the main thing. I wanted people to try that themselves to see if they could do that.
Yeah. So launch the poll.
Well, in principle, you could have a slider that changed the initial value of y.
Right.
As well.
So we can do that for sure. We have to modify our replot function and specify that we're gonna also specify the initial value of y. That one is, let's see what the typical values are. I mean, it goes from 0 to 20, 10 to the 10. But let's just do 0. Let's just do this. Let's just turn this into another slider, float slider. That starts at 0. The max is 20. The step size, this is fine. The 5, but then we'll multiply it here by 1 e to the 20. E to the 20? No, I'm sorry. That's the total number of hepatocytes. Okay. So let's see what that does. Okay, so now I can change what my initial number of y is. What is it doing? Here. It's running into a convergence error somewhere. Let's go to the oscillation part. So now I'm changing two parameters at the same time. Oh, I have this problem that I'm. Okay, now it makes sense. So now I can change where my y starts at. You guys can see how this number is going up. Why do we get that convergence error there?
Well, you're starting with y way out of its stable value.
Yeah.
So y is decreasing exceedingly rapidly at the beginning.
Oh yeah. Yep.
And that rapid decrease means that your step size is too big. So
right.
What you really want to do is start with y down here.
Is right. Well,
so
then I can make this 10.
There you go.
And my y limit, I'm gonna make it the same ranges as this. 0 to 20, e to the 20, e to the 10.
Now remember that's a multiplier, so you want it between 0 and 3. You're multiplying you don't want to multiply y by e to the 10, you'll get e to the 20. So if you're multiplying, make it just 0 to 3 or 0 to 5. Probably float it. So.
No, but that's gonna make it like literally 5. Yeah, we're literally, we need 5e to the 10 or something.
But you're multiplying.
I'm multiplying 20 by e to the minus 10. So that's a maximum value, e to the 10. So that's a maximum value of y.
So that should be okay.
Yeah, but the y limit here should be
it's the okay. Sorry, I misread what you were.
That's fine. 2e times 20. That's yeah. So now that controls where I'm starting my y value. And what happens to the oscillations when I always, in this case, because R0 is smaller than 7, I have no oscillation. So I always end at that fixed point. But how I get to that fixed point, how the oscillations are, depends on what the amplitudes of those oscillations are, depend on the initial condition of y. Now let's change R to get oscillatory values. And then now I can see that I'm spiraling it out or spiraling in. This is what we were talking about. So if I start outside of the limit cycle, I spiral in. If I start inside of the limit cycle, I spiral out. And you guys just took a whole dynamical system class in 15 minutes. And you can guys see the limit cycle there like quite clearly.
Do you want to give people time to replicate that?
Yeah, absolutely. I'm actually want to take a picture of this because it's kind of cool. Okay, I think we can keep going.
You want to take a quick break now and start back at?
Yeah, we can definitely do that. I think we should, after we could break out, and then you can work with to do this stuff with the people you were working last time, and then I can work with the people I was working to do the sliders on the plane, or do you want us to do together?
I think doing that analysis together is probably worthwhile.
Yeah,
Because
and
the stacking and the finding of the final values and counting things takes some effort.
okay, and I also want to walk people quickly over what I've done with my notebook as well. So, okay, let's take a break now and come back in 10 minutes. 10, 15 minutes.
Do you want to say 6:30?
Yeah.
7 minutes.
Yeah, that's fine. Okay. So just to recap, we started with a slider that allowed us to change R naught such that we could explore continuously the transition between this type of regime where we have a stable fixed point at the end of the simulation to this regime where we have stable oscillations at the end of the simulation. And we explained that so far we sort of like done that manually, but we can do it also interactively by wrapping the simulation inside a widget, inside a function, and specify the parameters as a widget. Then the next thing we did is that we, instead of looking at the simulation as a variable as a function of time, we started looking at the plane that has the values of x and y. And the idea is to show that when we start at a value that is below R naught below 7, x and y circle in, but it always finish at a specific point, which is what we call the fixed point right there. Let's see what happens when R naught is smaller than 0. What happens is that we end with no
Or no less than 1.
I'm sorry, less than 1. We end up with no infected cells at the end of the simulation, which is what we expect. What we expect when R naught is smaller than 1. Right. And then we also show that after a certain value of R naught, we end at a there. Oh, there. We spiral in and end at a stable oscillation. And if we change the value of no, I would have to change my value. No, let's see. Yeah, no, that's gonna work. And but I showed also that if we start at a inside, then if I start inside of that value, inside of that circle, I spiral out here. Yeah. So if I start inside of that circle, I spiral out until I reach the stable limit cycle, which is what happens in this case. If you see the arrows go in, spiral in until they reach this limit cycle here. If you're outside of it, if you're inside of it, they spiral out until they reach the limit cycle. So we're basically recreating this picture one slide at a time. There's sophisticated software out there that will allow you to reproduce this image. But the idea is that we are basically, as we move our node, we're basically sliding. We're sliding through this image here. We're getting different slides here, or cross sections here. Okay. So before I'm gonna take a break from this to show you how some of these sliders can be used to put together your applications that you're gonna submit as your final project. So I have an example. Coming back to the SIR model that we had at the SIR model that we fit to the data at the very beginning of class, in the first few classes. So again, this is a work in progress, so it's not finished, but so you can get an idea of how this can be put together to develop the application. So in this notebook, you guys have seen this notebook, but we've modified it to include sliders. So for example, here, now I have the option of uploading the data sets by changing the option in my drop-down menu. And then now I have this not finished, but the option of specifying what part of my graph I'm gonna use to calculate the parameter mu, and that one we calculated by looking at the slope on the downside of the curve. So now I choose a time interval where I'm gonna calculate this, and then I have a button that I press, and then that calculates mu for me. And I think I don't have the upside of the curve, but it's basically copying and pasting this code. So in terms of the type of cells that you might have that are available to you, you can change the type of your cell. Let's create a new cell here. By here, you can specify what type of entry the cell contains, what type of data that the cell contains. And Markdown is the one that allows you to specify text. And then there is some complicated formatting that comes with specifying how the text is gonna look like. But if you put a pound before the text, then Jupyter interprets that as the title of that cell. Then if you put 2 pounds, then interprets it as a subtitle. So this way you could create different, let's say, entries in your own notebook. But the thing is that then you cannot combine in the same cell, you cannot combine text and code the same, because that cell is just text. The other neat option is, and I actually don't even know how many levels you can create here. I guess it's as many as I don't know. I really don't. I haven't tested this. Yeah, so you can sort of like create sub levels. And then the other neat option is that for those of you who might be familiar with LaTeX, you can specify functions using the typical LaTeX syntax. I'm not going to spend time explaining LaTeX right now, but you can. I think, and I actually think that's the only way you specify. You can specify equations inside of these markdowns. And then if you want to have like at least an idea, I don't know, because I know the ones I use I know already. You would have to look at what the specific syntax is for specifying function, and I can look at it. Hold on. Let me be more.
Why not just search on LaTeX equation quick guide or something like that? I might give it to you. Overleaf is good because it is a WYSIWYG for the LaTeX folks.
So here it specifies it. You can, if you look at this overleaf allows you to type LaTeX code and compile it right there. So you can create an account there. And
maybe
then
share the link to over. Oh, you did just now. Yeah. Perfect. Thank you.
And then it shows you what the specific syntax is for the equations and so on. You don't. It doesn't have to be extremely. I mean, LaTeX can be as complicated or as simple as you want it to be. But just to get an idea of what the basic syntax is, in case you need to include LaTeX equations in your notebook, in your application. In any case, if you also if you're running into problems, you can feel free to email me, and then we can sort of like I can sort of like walk you through the basics of it. I wouldn't worry about that too much right now. But the idea here is the idea is to show that I can combine titles with text, with equations inside a single cell. But I need to specify that is a markdown. I can also insert images. To do that, let's come back to this equation. So I can include an image of what the simulation is going to look like. I'm sorry. To include images, I come to this little keyboard here, and there is a bunch of options that I can a lot of commands that I can add, that I can use that I can, that I can use here. Yeah. Oh, cool, a cheat sheet. Good. I should probably look that myself as well. Yeah, so here's the headings. Colors, bullets, number this, horizontal lines, even links if you want to add, and that's very useful. Thank you, James. But to add images, I can come to this using the GUI options. I can come here to this keyboard here. I look insert image. Why? Come on. I don't know if, I'm sorry. Do I have to be? Okay, yeah, so I think I have to have that cell to be marked down to be able to insert an image in it. And then now I can include an image. And there has to be ways of controlling the size and the aspect ratios on the images. I'm just not sure what those commands are. But yeah, this is a way that you would include images in your notebook. Okay. So
that last link that I pasted in is the syntax for the equations.
Okay.
That's not a compact place to look, but the things you need aren't that complicated. So
right. So if I wanted to, I could say, just as an example, I could specify them by looking at. Yeah, it can be a bit complicated. I sort of like know some of them already. Like that's the thing about LaTeX.
So you're not going to need much more than the fact that Greek letters are backslash in the name of the letter.
And then fractions.
And fractions, yes. And that you have to use curly brackets to put things to put superscripts and subscripts together. And
then you can be fancy and you can put times like this, but you might not need to. This is just as an example, so you guys see that it's not extremely complicated. Yeah, it's
backslash or frac.
Yeah. And then here I can dxdt. There you go. Not extremely complicated. If you wanted to add a subscript, you would add it. You add it with an underline. Let's call it AB here. And if you want to add a, is it how you call it, superscript?
Superscript.
Superscript, right? Then you add it like this. So I don't think you would need much more than this. Maybe you might need to know how to type the Greek letters, but it's basically you type slash and then the name of the Greek letter. And yep, so this is how you can integrate titles, equations, and images. I mean, that's a lot right there. To specify the size and aspect ratio of the images, there might be options to control that. I haven't tried them. I wouldn't think it's extremely complicated. Okay, any questions about that so far? Why don't you guys try loading an image to your notebook? Just take a screenshot of this part here, which is what I did. And then try creating a new cell, making sure that it's marked down, and then uploading the image.
And maybe try typing a simple equation too.
Yeah, that too. Just try to do these three things, so you get a familiarity how to. And of course, if you guys have questions, feel free to ask. Okay, I'm gonna keep going. So the last thing that might be useful for you to use as you develop as you turn your model into a Jupyter app is that Jupyter has NanoHub allows you to display to turn your the code that you have into app mode, which is basically how the code would look like once it's turned into an application. And here is an example. So here is how the application looks like. Disregard this. This is just a working version. But then you can see that the code is hidden, so it's not available to the user. What is available to the user is the widgets that you've created. So as now the widget, this is available to the user in terms of what data set the user can play with. And then the other widgets that are also created that you've also incorporated into your code are also available to the user. At the moment, we're still trying to figure out some of this stuff. So for example, you guys see that when I changed the data setup here, it didn't change anything down here. There has to be a way of connecting once you change, let's say something up, every other cell down resets. We'll still working that with Andy, which is the local expert, but we'll figure that out. So see, when I changed the values, then it changed the data set, but I had to reset the values. And it's still kind of odd because of the maximum still corresponds to the previous version. But yeah. So there's a little bit of errors that need to be, not errors, but small details that need to be fleshed out. But you can still start to construct your application while we figured out some of these small details. And then the last thing I wanted to say is that there is if you go to the Jupyter widgets, that also allows you to specify certain layouts. You guys see that in this particular application, everything is kind of like one below the other, like exactly as in the notebook was, exactly as the notebook was written, the data is being displayed. But I might want to have, let's say, this plot here around, so it's besides the text instead of below it, so as to make the app look better. You can do that with the widgets, with the widgets, with the layouts, and this is also, yeah, this is also some. We're still working with this, but yeah. So just to so you have an example here of how the layout allows you to put stuff besides the other. Let's see. Yeah. Okay. Cool. Again, is as you see, there is a lot of stuff that you can use. It's very versatile in terms of what widgets you have, how do you combine them. that is all. What widgets you use are going to depend on what control the user is going to have over the model parameters or over certain aspects of the model. Yeah, so you here can see a lot of the widgets that are available to you. Okay, so yeah. Oh, and then if once I'm in application in the app mode, I can get out of the out mode by hitting edit app, and it's gonna take me back to my notebook. And I again, as a reminder, the notebook that is gonna be displayed in your app mode is the last one you saved. So if you, let's say, type stuff, go to app mode, the stuff that you typed that if you didn't save, it's not gonna show up in your app mode. And even worse, when you come back to the app, that is going to be lost because it's going to reset to the last checkpoint. So before hitting app mode, make sure that you save and checkpoint so you don't lose any progress that you might have incorporated into the notebook. Okay. So now let's come back to the model that we were working with. So in your homework, one of the questions we had was, well, last time in class we were trying to replicate this curve. The problem here is that the code is doing a lot of stuff at the same time. But let's just do a simple version of the model. Let's just break this down. So how do I get this plot? This plot is showing the final values it's showing the fixed points of my model as a function of my parameter or not, right? It's showing whether I end at, where did it go? No kernel. Okay. Right, it's showing whether I finish at a fixed steady state or at a limit cycle where I have these stable oscillations. So to be able to generate that plot, I need to be able to record to see what happens at the end of my simulation. And if at the end of my simulation I have one fixed value, then that fixed value indicates that I have a fixed point. And if I have oscillations, then I have to be able to record what the maximum and minimum of those oscillations are, because that's what's indicated in this plot. This plot is basically showing the amplitude of your oscillations, showing the maximum and minimum values. So let's start with generating this plot. So the first thing I want to do is I want to be able to iterate through different values of R naught. And in this case, I'm going to go from 0 to, let's say 13, 0.1. So this divided by this is going to tell me this divided by this is going to tell me how many times my model is going to simulate. So if I make it too small, I get better resolution, but it's going to take a lot of time because it has to simulate the model that many times. So what I need to do is I need to load the model.
I guess what I'd suggest, Josh, maybe is show them how to do the first one and then let people try the other two.
Yeah, that's fine. The other two are a little bit more complicated, but yeah, we can break apart or something. We can, yeah, I think a breakout room would be good for that because then I can work with a couple of them and then you can work with a couple, and then that way everyone gets to work. So we're gonna simulate the model. We're gonna load the model and we're gonna simulate it. And although here they simulated until 800, we probably want to simulate it a bit longer because what we care about here is not necessarily the time courses of the model, but really what's happening at the end after I run the model and the model sort of equilibrates to certain values. So let's just run it to 1600. And really what this value is, if we look at what that value is the total hepatocytes, which in our model, in our equation, in our untitled string, we have already specified as T. So we're just going to do that one. And again, as I've been mentioning, what we care really is what happens at the tail of the model, at the end of the model. So let's initiate a variable that is called tail, and
why can't you just use, maybe we should ask the question for the students, why can't you just use the final value of T?
Let's try it to see what we get. So I keep saying this. What we care about is the steady state. What happens at the end, right? So let's record what happens at the end of the simulation. Let's call it endpoint, and that is the last value.
Or just M of T, M dot T.
Right, or that too. And then what I really want to do to generate this plot is to be able to have an array that has R naught and then the values of MT. So I'm just going to call it BP for bifurcation plot. I create an empty array that has that the shape has a shape 0, 2, which means that takes it has no columns, but it has it has no rows, but it has 2 columns. And then as I iterate through this loop, what I want to do is I want to stack each of the values, R naught, and then the final value of T. So basically what I'm doing is, let me draw here. I created a placeholder that allows me to stack in anything I want but that has at least 2 columns. That's the maximum columns that I can add. So basically, what I want is every time I specify an R naught, let's call this R naught equals 1, then I want to be able to stack the value 1, the value of R naught, and then my empty for that value, my final value of T. Then as I change my R naught again to, then this array now becomes this. And so on, so on, so on. So the way I do that is with the function called vstack. And the function takes a tuple as an input, which is whatever I want to stack to, and then as another tuple, my value of R naught, and then my final value of T. Then after I'm done with my loop, then I can plot this array that I just created. Let's see. Is it running?
Okay, everybody, what did he forget?
What did I forget? Oh, yeah.
You forgot something important. Let's see if people can catch.
Yeah, I saw.
Oh, never mind.
No.
There's a line missing. What is it?
Yep.
Maybe remind people of what you're trying to do.
So I'm trying to assign different values to the variable or to the parameter R naught in the model. So I'm iterating through a loop, right, to assign that value. But although I'm iterating through the loop,
Value isn't getting reassigned.
the value is not being reassigned, right? So to do that, I need to make sure that I reassign the model, the value. So I load the model, I reassign the value, and then I simulate the model. Okay, let's run that again. It does take some time. Okay, so what do you guys see here compared to this plot? Let's actually make it even smaller. It's gonna take a little bit, but a minute, but it's easier to explain it that way.
That's one where you could test whether doing reset is faster than doing reload.
True. It's supposed to be 10 times smaller, 10 times slower, but this doesn't seem like to be 10 times slower. Let's see. There. Okay, what do you guys see here? What's happening? Okay, what is the difference between this plot and this plot?
Seems to be filling in the space.
Right. It's filling up the space here, right? Because this line corresponds to the maximum value in my oscillations. And this line corresponds to the minimum value of the oscillation. But what I'm recording, I'm not recording that. What I'm recording is the final value. And the final value, when in those oscillations, it can lie in between those values. It's in any point between those values, right? So that's what you're seeing here. You're seeing for all of those that are in between is that at the end of my simulation, the time course was in between the maximum and the minimum of the oscillation. Does that make sense? Okay, cool. So to be able to fix that, instead, well, let's see. I'm gonna ask you guys, instead of how could I fix it? Because what I want is a line here and a line here, which corresponds to the maximum and the minimum in the oscillations. I mean, that's kind of like the answer.
I mean, we write some function to find the extrema based on like what the relative values are, and then we like put those in an array and plot them instead.
Yep, absolutely. So instead of recording the final value, I need to be able to look at the oscillatory part, and then take the maximum and the minimum of those oscillations.
So before you do that,
yep.
Can you just take the max and the min of the time series?
Oh,
if you took the maximum of t, what would happen? And the minimum of t, what would happen?
Right.
You could plot that, Josh. You could have everybody do that together. So
okay.
You have to add one more column here and here, and then plot the max and min.
So instead of plotting the final value, what I want is, let's call it MA. What I want is the maximum of T. And then I can add it here. By the way, I defined that. It's different. Oh wait, I did something wrong here. Okay. So now I have 3 columns, and then I'm adding 3 different data. Okay. Oh, that's the one that runs slow. Can I interrupt the interrupt the kernel? Okay. So that doesn't work, right? You're muted.
Why doesn't it work?
well, we're finding just the one maximum, right? We're not finding like the maximum of like each individual oscillation.
Well, yes, you're looking at the maximum of the whole data set. But
Maybe look back at the time series.
Right here, this one.
And you see that the initial value of t is very large, and then the steady state value of t is much smaller. And the initial value of t is always the same, and the final value is always less than that. So if you take the maximum over this whole time series, you're always going to get that initial value.
Right. So instead of doing the maximum of the whole times course, we need to, let me draw here. We need to sort of slice our time course and look at the area that we have the oscillations, and then take the maximum and the minimum of those oscillations. And here is where, that's why we talked about running the model for long enough, because from this plot, we get the sense that the amplitude of the oscillations is increasing as I increase R naught. So I have to run the model enough so at least I get a full oscillation, because that amplitude is increasing with R naught. So instead of doing this, we're close, but we're not there yet. What we need to do is to take a smaller area, we need to slice the data such that we take, let's say, the last 2000. And there is, I don't know, there's a systematic way of doing this. We basically did it just testing how big the slice was, but
maybe we remind people what that minus 2000 does.
The minus 2000 dot takes the last 2000 point. It slices your data from the 2000 from the last one till the last one. So we're basically cutting it this way. We're saying, okay, I want the 2000 point before the last one till all the way through the last one. And then what I'm doing now is that I'm taking the minimum and the maximum of that, and then I'm plotting the minimum and the maximum. So there's actually, the way it works is that it overlays two plots, right? Because I need one plot to represent the line that goes to the minimum, right? Because those are all the minimum values, and another line that shows the maximums. The maximum and the minimum are the same in the areas that you have no bifurcation, no oscillations, but they are different once the oscillations start. So that's why they overlaid in this region, but then they separate in this region. And then after a certain value, then those oscillations dissipate. Actually, let me do something. I'm actually gonna run for longer just to make sure that it's not that the amplitude is, the period is so big that it's not getting caught up by the, yeah, so it's not. I mean, in principle, I could run it for much longer, but it's fine. Okay.
You want to make sure everybody can get that to work?
Yes, absolutely. And that's gonna, yeah, that probably will take a couple of minutes too.
So if for people who got that quickly, why don't you add a very simple extension, which is plot the amplitude of the oscillations as well. That only takes one extra line.
Well, two, because but you probably need to include another column. Yeah. So you would change here to 4 just to make sure that you can add another data set. Well, but you might not want to overlay them because you might want to create a different plot. Let's just, so guys, so people who finished it, so let's call it 31 A for amplitude, and then you need just 2, and then here you stack it the same way, but you need something else. You're gonna need to define the amplitude. You need to define that somehow. That's the exercise, and then here you plug A. So I added 3 lines of code. You have to add 1 more to find the amplitude. Oh, I'm sorry, it's A. You have to think about what the amplitude is. What the amplitude of the oscillations is. And as a quick reminder, amplitude refers to this of the oscillations.
Wait, the height of the whole wave or half of it?
It's the whole wave, right?
I mean, if we have the maximum and the minimum, like numeric values, and we're trying to find the height of the whole thing, do we add? Well, no.
You're close, but it's not that operation.
Oh, subtract them.
Yep. So we already know the max and the min. So to get the amplitude, that is just the maximum minus the minimum. And now we're looking at the amplitude of the oscillations as a function of R naught. Let me rerun it. Okay, so I think the last part we want to do is we measure now the amplitude of the oscillations. Now we want to measure the period of the oscillations as a function of R naught. And a period of the oscillation refers to this.
So maybe it's worth discussing as a group, how could you find the period of the oscillation?
Yeah, that's a good idea. In terms of thinking in terms of this.
If you have the time series like this, how would you find this length here, this period?
So yeah, let's just add the axis here. This is time. And this is whatever, t, for the total number of cells. So how do I measure the period? The period corresponds to the time in which the time that it takes for the oscillation to repeat.
I mean, this is important because quite a few people are doing projects which have oscillations in them. And so if you have oscillations, finding the period of the oscillation is something you almost always want to do. And so thinking about how to do that numerically is useful. What are some landmarks I could use to measure the period? Maybe sometimes people don't want to talk because they think it's harder than it is. Sometimes the answers to questions are very simple.
Yeah, I mean the answer is in the image already.
Just the extrema, either the maxima or the minima, you can pick one.
Right. So I just need to measure the time between minima or maxima or whatever. I mean, that's one way. You can do it other ways as well. You can get it complicated. You can get the midpoint and then the times between the midpoint. But that requires a little bit more, probably a little bit more computational than just, since we already have the maximums. Okay.
So how could I find, sorry,
yeah.
Go ahead.
No, go ahead. Go ahead.
How could I find a point that is the maximal value? What's the definition of the relationship between this point and its neighbors if it's maximal?
The relation between this and this part.
Remember, my data set looks like two lists, a list of times and a list of values. Maybe you could draw, Josh, you could sort of draw your table again.
Yeah, that's a little bit harder with this thing, but I'll try.
I could do it since I have a drawing pad, right? So I'll do it.
Here, I draw the table for you now already. So again, what defines the maximum point in terms of the relation with its neighbors?
It is greater than its neighbors.
Right. So to find the maximum in this list, I need to be able to compare this point to the point before it and this point to the point after it. And then if it's bigger than both of those numbers, then that is a maximum. Does that make sense?
Yes.
Good. Okay. So then I have to iterate over each point of this list and compare it to its previous neighbor and to its following neighbor. And if it's bigger than its neighbors, then I know, okay, that is a maximum. If I want to detect the minima, it's the opposite. Both of its neighbors are bigger than that number. But we'll just stick with the maximum for now. So So let's just start with something quite crude for the moment. So what I need, as I said, what I need to do, I have my times and I have my values of the number of hepatocytes. So I need to iterate through my number of hepatocytes. The only problem is that I don't always get oscillations, right? And I don't know how we solved this in the previous quarter. Let's see. Yeah, it's a little bit of a
I wouldn't worry about that first. Let's find the oscillation period, and then we can discuss what you need to do to clean it up.
right. Okay, so I know that I get the oscillations, that this gives me the right slice of this table, where I actually get oscillations, because I don't get oscillations for times before. I don't necessarily get oscillation for times before that. So I'm gonna call that the tail of my time course. Again, I'm just slicing the data set. So now I need to, let me just move this up. So now I have something that looks like this, right? Like this column. So what I need to do is I need to be able to iterate through each item of this table and compare it to its previous neighbor and to its following neighbor. So I'm going to create a loop. Yeah, I'm going to create a range that goes from 1, and the reason it goes from 1 is because 0 is the first one, and I don't compare that one to anyone else. So I need to start from the second for the second time point in my list.
Quick question on that, actually. I
Yep.
know it's not the case in this data set, but what if but if you did have a data set, say, that was like a cosine function and our first point's going to be at the maximum at that first index, then would we have to account for the edge case where the maximum or the extrema is like the first data point? Like, I know we don't have that here, but
Right, but then you have to add it you have to add, like, measure the endpoints independently, because in those are specific cases. So you just compare that point to its neighbor, but you might also want to compare it like to the rest of the list to make sure that that is an actual maxima. But that is a good question. I haven't thought about it. Let's say you have a cosine function and you don't necessarily start, it's shifted, so you don't start at the maximum. You want to compare that value that you start at to the first maximum that you compare, that you find, and then if it's the same, then you know that you start at a maximum. If not, you know that you started somewhere in between.
all right.
But yeah, does that make sense?
Yeah.
Okay.
I mean, it's also true that if you're really only, if the thing is really periodic, you only have to measure the period once anywhere in the oscillation.
Right.
And so if you can find 2 successive maxima, you're done.
Right.
If there's some possibility that the frequency is changing a little bit, then you might want to average the period.
Right.
And then you have to do more than one.
And if what you're really interested is in finding all the maxima, then in that case it might be that problem might be then important. But again, what I need to do is iterate through this list and compare each item in the list to its neighbor before and after. So what I'm doing is, so I have the item, and then I need to compare it to its previous neighbor. And I need to compare it to its following neighbor. I mean, we can make this as complicated as we want, but right. And then we said that if we want to detect the maxima, this one has to be bigger than its previous neighbor. And it also has to be bigger than its neighbor that follows it. So I can make this a condition here. And then a condition here. I can do this or make it an and. It doesn't matter. Okay. And now, what do we do? So I corresponds to the index of that of the index of the maxima. So I know if I plug that index into my time, then it should correspond to the maxima, to the time at which the maxima occurs. So let's call them max times and just make it an empty list. And then what I can do is I can append the index. But there is, and this is a complication that you didn't want me to go into. This it corresponds to tail. It's iterating through tail, but tail is shorter than time. I mean, one way of solving this is just to do this because we can slice time slice time the same way. Let's say tail times.
You're missing a colon in your slice.
Yep, I just noticed it. And this makes it quite straightforward. So now I slice both my data set corresponding to the total number of cells, and I slice the time. And now what I want to append to this list is the times at which these maximums are occurring. And then let's just, for the sake of it, print this max times. Okay, but let's shorten this. Instead of going from 0 to 13, let's choose a region where I get the oscillations. Let's go from 8 to 9. Okay. I wonder why they're changing so drastically. And in no particular.
I think you'd have to look at the time series to know that.
Yeah.
It may be that the number of points is not enough for the
Right. So that's a Yeah, that's a good question. Let's see. That's a lot of points.
It's still different. So I guess the oscillation frequency hasn't settled down yet.
Right.
But you can still go ahead and because we're going to run out of time.
Right. So what's happening is that the oscillation is not settled yet. I can run the simulation for longer to make sure that the oscillation settles down. Or in this case, I'll just take the maximum value of the or the average value of that. And what I'm gonna do is I'm gonna period.
Oh, wait a second, Josh.
Yeah.
You didn't take the differences yet.
On what?
Of the times.
Oh, right. So the period is the distance, the difference in between this time and this time, right? Because what I recorded, I'm sorry, I have 7 minutes and I'm trying to finish this. So what I recorded is basically what I basically recorded was I first found the maximums, and then I found the times corresponding to those maximums, and those are the values that you're seeing there. The period, to find the period, I need to find this part, right? Which is the difference between one point and the other. So that's maybe why we're not looking right.
That's it. And when
Yeah.
you take the diff, you'll be fine.
Right. So what did I do wrong? Oh, here. Yeah, it's right. There is a little bit of a difference, but it's mostly settled. It's mostly settled. Let's do 6,000. Yeah, we're very close. So we're just gonna take the average of this. So we basically took the difference between each of my between T2 minus T1, T3 minus T2. That's what this MP.diff is doing. So it's varying a little bit because of the numerical differences, how many points I have to calculate the distance here. What I'm gonna do is that I'm gonna take the average of that as the period of my oscillations. MP mean, I'm sorry. So that is the period of my oscillations. And then now I can record it as a function of R naught. Let's call it. Then I can try to plot yeah, and let's start in the section that in the area that I know I have oscillations. Did I have where's what is it?
Hypo,
Um,
beef stack.
yeah, but there seems to be another.
You're missing a parenthesis, close parenthesis.
Right. So now we're just looking at the area where I have the oscillations. So that's why it looks like this. And then I can see that the amplitude of the oscillations increase, and then goes to 0, whereas the period of the oscillation increases until I get to this area where I have no, no oscillation. So it has no periodicity. The period is 0. Okay. Yeah, I'm gonna stop there because it's 7:58. But this covers at least 2 or 3 parts of your homework. Any questions up to here? So James is gonna be available next week. I'm gonna be available till Wednesday, and then I'll be available again after Saturday. So if you guys have any question regarding your project, need any help, either with the model or turn it into a Jupyter app, don't hesitate to contact me. And James, take it away so you can say the.
Okay, well, thank you. Yes, Fabi, your homework is finishing what you haven't done of the homework we are already assigned, and then working on your projects. Because we only really have 2 lectures to go. Yes, we have 3 lectures after Thanksgiving, of which the 7 people, really 2 of those lectures should be you speaking, which means we really only have 1 lecture to go. So that means that people need to have their projects ready in basically 1 week from today, 2 weeks from today, 3 weeks from today. At least some of you need to be ready. And so that doesn't give us that much time to get things finished. So please meet with me, meet with Josh. And we wanted to spend this extra lecture trying to go over some of the issues you might face when you're trying to put the projects together. I hope it was helpful to see how to think through some of these problems. Again, knowing what people are working on for their projects, I think most of the issues that we've dealt with here and some of these little code methods are things that you'll use. And so with that, I guess we're done, unless there's specific questions. Any questions before we break tonight? Okay, well, thank you. But happy to talk to people before or during for me, the holiday doesn't exist, except that we don't meet for class next week unless you really want to have an extra class on Tuesday before Thanksgiving. But I'm happy to meet with people this week and next week. Okay, thank you, everybody.
Yeah, happy Thanksgiving.
Thank you.
Happy Thanksgiving. Okay.
Thank you.
Have a good Thanksgiving.